Okay, this is hour 2 for Physics 1C on May 19th. Today we're talking about, or now we're going to be talking about induced electric fields. Now, for this, if we were in class, I would definitely try to draw this picture on the board. But on this system, I am really worried that there's no way I can draw this as well as it's already been done in this diagram. So I'm going to use this diagram right here, and I'm going to give you some time to digest it. I don't want to go too fast here. So this is our scenario. We have a blue cylinder, okay, that's wrapped with a wire. Okay, so you've got a black wire going around and around and around and around and around like that, right? Now this wire, it has current in it, but the current is also changing with time. It's either increasing or decreasing. Okay, in this case, I think with the way that the picture's drawn, the current, at least at this moment in time, I believe. No, it's increasing. I'll show you why. That means di dt, the rate at which the current is changing, is positive. Greater than 0. Okay? The current's increasing, di dt is greater than 0, right? So now, surrounding our solenoid is another wire connected to a galvanometer. Okay, this wire is just, it doesn't have any EMF source, let's say, attached to it. A galvanometer is just, it's a something that measures current. Okay, that's all it is. And I think, unfortunately, we never got to do a lab where you got to use one of these, but it basically measures current. Okay, it could be a multimeter. It could be, let me get to where I can see your guys' questions if you have some. So, does the picture make sense to you guys? If you look at the way that the current is flowing, if you wrap your fingers of your right hand in the direction that this current is flowing like this, you'll see that your thumb points in that direction. So that gives you the direction of the magnetic field, right? Because a solenoid that has current flowing in it creates a magnetic field. But this magnetic field is changing in time, right? It's changing in time. So it's worth mentioning. Because that implies that there's going to be flux through this coil here that's also going to be changing in time. Now, it's very easy to look at it's a lot easier to look at the picture from this perspective here. This is basically the end view. It's basically like you'd be looking from this end right here with your eyeballs. So you'd see a magnetic field going inwards. You'd see the current flowing around on the inner wire in that direction there. And you'd see your ring right here, okay? And what we want to talk about is what's going on inside the ring. So according to Faraday's law, right, we know that there's going to be an induced EMF in a system if we take negative n times the change of the flux through the system. You guys remember this? It's been a couple weeks. Faraday's law says you take n, where n would be the number of turns in this guy, multiplied by the flux through that object, right? Okay. Now notice that this has an area A on the end right here. So this whole thing has an area A right here. And what we can do is we can say our flux then is going to be equal to n times ddt of the magnetic field multiplied by the area. And then if we think about the way this is going to work out, then it's going to be negative n times b times a. The magnetic field of a solenoid, of a system like this, you guys remember what this is? The magnetic field of our solenoid is equal to mu naught multiplied by the number of turns per unit length, and then multiplied by the current that's flowing through the solenoid. That's the magnetic field that we're going to get out of this. So this is going to become negative n multiplied by ddt of mu naught little n times I, and then times the area. Now all of these things are going to be constant except for one thing. So we end up getting negative n times mu naught times the area times little n, the number of turns per unit length that's in this guy, and then we multiply by di dt. Now, because di dt is increasing, that's why the current is flowing in the opposite direction to the external current, right? The current here flows this way, but the current in the other system in the ring is actually going to go this way, the current we call I prime, where I prime is basically equal to E over the resistance of the loop. So if this loop has a resistance total that we call R, then we take this EMF that we have right here, divide by that resistance, and it would give us the what's going on in the system right there, right? Now, when we look at the system, okay, and we say, okay, what's actually happening within this wire right here, right? So with the way that we've set this up, you could legitimately ask the question, what is, I'll write it down, what's actually causing the charges to move, okay? Does that question make sense? We know that magnetic fields can cause charges to move, right? We have this force, magnetic force, that's given by the charge multiplied by the velocity crossed with B. We know that a magnetic field can actually cause charges to move, right? But there's no magnetic field out here, right? Or there's a very weak one. So you can't really say that it's the magnetic field that's actually causing the charges to move. I mean, maybe you could. Maybe there's a way you can say it from some perspective. Be a different reference frame or something like that. But the magnetic field doesn't even exist out here. It's only in this region, right? So it can't really be the magnetic field that makes the charges move. And so the idea is these pink arrows right here represent the fact that there must be some electric field at that location. Does that make sense? There must be an electric field there. And to understand where that electric field, what it's going to be, we have to remember the following statement. The EMF that's produced, in any case, is equal to the line integral of this. That's the value of the EMF in our system. You take the integral of E dot ds, and I think you have to do it around a closed loop, basically. So if we compare this to what we've done up here, we have another expression that says that the integral of E dot ds is equal to the time rate of change of the flux. And this allows us to compare directly the electric field to the magnetic field. And that's pretty cool if you look at what that equation says right there. It basically tells us that if I have a system in which the net flux is changing with respect to time, then I'm going to get an electric field that's produced within that region. Does it make sense? The fact that this flux changes induces an electric field at the location of the wire. Does that make sense? One way you could put this into words is to say, and I kind of want to just type this. And these changes in magnetic flux, they induce electric fields in the space all around. So there's technically also an electric field that's induced a little farther out. We'll get to that in a second. Like, meaning I could draw a line around here and say there's actually an electric field out here. It's just a little bit weaker, right? So Whoops. Control Y. There we go. Let's apply what we did here. So if we look at this line right here, we can say that if we want to do the line integral of E dot ds around our loop, that this is going to be equal to, as we said above here, negative n mu naught area, number of turns per unit length, multiplied by di dt. And then what we do is this. We say, this is a line integral, right? So really all we need to do is to have something to represent the path, ds, and then notice that the electric field is going to point in the same direction as the path all over. Oh, actually, I think what we do in this case is we orient our path opposite. It's not super important in this case, but this gets rid of the negative sign. We do this because you want your path to go in the same direction as the magnetic fields, meaning if you point your thumb in the direction of the magnetic fields, the path is going to be opposite to that. The effect of that is going to be that the left-hand side of this equation right here is just going to end up being E times ds, but it's going to be negative. It's going to be the integral over a closed path of just ds, and this is going to end up being negative E times 2 pi r, where r is going to represent, well, it's written right there, it's the radius of our path of the loop, right? And that's going to be equal to everything on the right-hand side, so we eventually get the following answer. The electric field that's created due to this solenoid that has this changing current ends up being equal to n times mu naught times the area of, this was the area of this thing, remember? That's A, multiplied by little n, and then divided by 2 pi r, multiplied by the time rate of change of the current. That's what the electric field that's produced there is going to look like. And we'll do a calculation here in a second with a problem. Now, it's a very special type of electric field, by the way. Like, this electric field is very different. I want you to think about the following scenario. Let's take a really simple circuit. And I guess we can put a resistor in here. So we've got an EMF source and we have a resistor, right? Let's say that I start at a point, like right here, for example, and we call that point A. And we want to basically go around the loop, and we want to calculate what is the integral of E dot ds equal to. Okay? ds is going to be going this way. And we're going to say that if the current flows in the system this way, that also means the electric field within our wire has to look like this, right? What's this equal to in this case? Well, I start from A and I go past the EMF source, right? So my E dot ds now is going to give me the EMF E. I keep going around in a circle and I pass through here. And I say, okay, well, if the current in my circuit is I, then I'm going to get minus IR here. And then I go back around to the original point again. What is this equal to? Think back to some of the laws we've learned about. In this circuit, what is this equal to? It's 0. Exactly, Quincy. It's 0. So in, we call this like a normal DC circuit or something like that. You could say in general that E dot ds around a closed path is always 0. Okay? Unless you have this stuff going on. The moment you have a flux that's changing, this isn't true anymore. You guys see what I mean? This is basically proof that Kirchhoff's law, the law about sum of all voltage drops is equal to 0, it's actually not complete. It's actually not complete. This is the more correct version of Kirchhoff's law, the complete version of Kirchhoff's law, the complete version of Faraday's law. It turns out that Kirchhoff's law is really just Faraday's law. It's Faraday's law when there's no flux changes, right? You guys see what I mean? So this is the more permanent form of Faraday's law right here. It relates the electric field that's produced to the change in magnetic flux. And you can use it to exactly figure out what that electric field would be. And I know this is a bunch of mess right here, but this is what I want you to notice. The electric field basically falls off as 1 over r, right? So let's say that we take our system here where we've got our magnetic field, right? And we go to different locations. The electric field at this ring is going to be strong, but then when you get out here, you're going to get a little bit of a weaker electric field, right? So you might say, okay, here my electric field is really strong, but then in the outer one here, the electric field is just a little bit weaker. But you have these circular electric fields that are basically produced within this regime right here, right? And those circular fields have this special effect that when you do the integral of E dot ds, you don't get 0 anymore. You actually get the EMF in this case. So this type of electric field is often called a non-electrostatic field. The reason for that is there's no way to produce these type... This is what the electric field lines look like now, basically. You understand? They're circles. These are the electric field lines now. We've created circular electric field lines. There's no way to do this just by using point charges. So we call this a non-electrostatic field. Because there's no way you could produce it by just static point charges. There's no way you could do it. You can try as hard as you want. It's impossible. Okay. Does this make sense to you guys? Does anyone have any questions? I know this is really complicated. Okay, I think I have a problem we can do. This one. So in this figure here, it says, suppose that the solenoid has 500 turns per meter. Okay, that's little n. Cross-sectional area of 4 centimeters squared. So the area is going to be, what is that going to be? 4 times 10 to the negative 4 meters squared. Because the centimeter is 10 to the negative 2, and you have to square it, so you get to the negative 4. The current in its windings is increasing at 400 amps per second, so that's the rate of change of the current. So that's 400. Find the magnitude of the induced EMF in the wire loop outside the solenoid. Okay, well that's really easy. That's that equation right there. We already did all the work. We just need to plug in the numbers, right? So our EMF is going to be, so big N is basically equal to 1 in this case. The EMF is going to be equal to negative mu naught. Mu naught is 4 pi times 10 to the minus 7 Tesla meter over amp. And then we multiply by what area A, so that's 4 times 10 to the negative 4. If you guys can calculate this for me as I'm writing all this out. We multiply by little n, which is 500. I'll just say meter to the negative 1. Turns is an actual unit. And we multiply by di dt, which is 400 amps per second. And all of that together is going to give us an answer for what the current in our circuit is. Just plugging this into my calculator. Can you guys tell me what you get if you plug all these numbers in? Oh. Really? Did I leave something out? Let me try it again. I got something a little different. What did other people get? I got like 1 times 10 to the negative 4. Yeah, that's what I got too. So I got basically 1 times 10 to the negative 4, and then EMF is going to be in volts. Amps cancel, meters cancel. I hope that unit's right. Sometimes I mess that unit up. Okay. Okay, now this is going to bother me. We have Tesla meter, an amp, and an amp. So what are we left with? The meters cancel. So we're left with T m squared divided by S. Okay, I think that's a volt. I'm almost certain that's a volt because a Tesla... I feel like this is helpful to just remember. So how do you figure out what a Tesla is? Well, a Tesla is given by this expression. And B then has the units of what newtons divided by Q is coulombs times meters per second, basically, right? So if we put that, or the other way to put it is it's basically newtons divided by amp meters. So if we plug that in here, you're going to get Newton over amp meter, multiply by meters squared, and then divide by seconds. And what we get now is going to be, well, amps over seconds. You know, an amp over a second would be equal to a coulomb. Yes, no. It's seconds over amps. My bad. Yeah, let's just not skip steps. Okay, what do we have? We have newtons. One of the meters cancels. We push the amps to the bottom, so we have amps times seconds. And then amps times seconds is a coulomb. And newtons times meters is a joule. And so that's a volt. So Tesla meter squared per second is also a volt. You know what I could have done is just not be stupid and realize that this is exactly what this expression says. Right? If you think about it. Like that's... these are the units of flux per time, right? Because flux has units of Teslas times meters squared, and time is seconds, right? So that would have been a lot easier way to do it. Anyway, there you go. That's part A. For part B, it says, to find the magnitude of the induced electric field within the loop if its radius is 2 centimeters. Okay, so this turns out to be really easy to do now, because quite literally, we just calculated the right-hand side of this equation right here, and our goal is to get the field. So what I'm going to do is I'm going to start from this equation. No, we have it right here, basically, right? Oh no. What's the best way to put it? Here's the best way to say it. So we have this expression that says the integral of E dot ds, right, is equal to negative n times d phi dt. Okay, so this thing is also equal to EMF, and we just calculated EMF. So basically, if we do E times 2 pi r for the left-hand side, where little r is going to be equal to 2 centimeters, so 2 times 10 to the negative 2 meters, this is going to be equal to the EMF. So that means the electric field is basically just equal to the EMF divided by 2 pi r. So in this case, it's going to be equal to the EMF, which is 1 times 10 to the negative 4 volts, divided by 2 pi, and divided by 2 times 10 to the negative 2 meters. And then because we get volts per meter, we're going to get, well, it's volts per meter is one of the units, and we just calculate that. And so I got 4 times 10 to the negative 4. Okay, that's the electric field. And again, it's this type of electric field that's like a circle, where at the center right here you have your magnetic field. And that field gets weaker and weaker the farther away you go. Just the this is something where I want you guys to think about. Okay, but wait, I gotta slow down. Sorry. Do you guys have any questions? So I want you to think about something kind of as deeply as you want to here, but I want you to consider what we've just basically said. What we've effectively just said here, and I'll use a lot of space for this, is suppose that I take a ring of where I've got a magnetic field contained within that system, right? And then we tell you somehow in some way that this magnetic field is changing, right? So dB dt basically is not equal to 0. This magnetic field is changing in some way, right? What we've just learned is that if I draw a circle out here, I don't want to change it to a different color. I put the center of my circle right at the center of the ring. What we've just found is there's quite literally an electric field. Whoops. There's quite literally an electric field in this space that does this, right? Just kind of like this. And if I was to go out to a bigger circle, well then there's quite literally an electric field there as well. And I'm not even talking about suppose there's a wire here. I'm saying in space, in empty space, if you were to have a device like the solenoid and you had the magnetic field changing in some way, then quite literally in the space around it, there would be this electric field that's produced. Does that make sense to you guys? Sorry about that. I don't know why it's coming up right now. Does this make sense to you guys? Does it matter to you? I don't know if this even matters to you. But this is extremely relevant when it comes to understanding what electromagnetic waves are. That's where we're going with all of this stuff. Is that the mere fact that you have a changing magnetic field quite literally produces an electric field in the surrounding space. And the type of electric field that it produces is the circular field. And we'll talk more about like some things here, but like it's important that you understand that just in the space around the thing, there is an electric field. Now, whether there's charges there to like be influenced by it, or whether there's a ring of like wire that's there to have charges move, it doesn't matter. There's still an electric field there, basically, right? And that electric field basically carries energy with it. All right. Do you guys have any questions? Okay. So, make sure I didn't leave anything out. Nope. It looks like we're ready to talk about displacement current. I'm going to attempt to draw a picture here. It's going to be awful, but I'm going to do it just because I think the drawing is helpful to learning. I want you to think about the following scenario. I have a system where I've got a capacitor, okay? And so here's my capacitor plate right here. There's one capacitor plate. It's attached to a wire, right? And then over here I've got another capacitor plate. I need to leave more room. So another capacitor plate right here. They're circular, and they're separated by some distance. Okay, so here's my second capacitor plate. It's connected by a wire, and it's connected up to an EMF source. And to keep things simple, what we'll do is we'll just take this and just put, I don't know if I want to do, I kind of want to make this an AC source, but we don't have to do that, I guess. Suppose I have a switch here, and suppose that the initial charge on my capacitor here is 0, and we throw the switch down like this so that we reconnect it. Current is going to flow in the system in this direction, and this object right here is going to start charging up. And at a moment in time, it's going to carry a charge that we call positive Q on this side, and it's going to carry a charge negative Q on this side. So this represents the charge as a function of time. This Q. It's like the charge at a moment in time, I should say. And now what we do is we're going to use Ampere's law to understand what's happening in our circuit here. What is Ampere's law? Ampere's law says that if I want to understand what's happening in a circuit like this, and I want to know something about the magnetic field that's produced, I need to draw a loop around my wire and then say, okay, well, within my wire, I know that the current is flowing basically from this direction to this direction, right? And at that location, there's going to be a magnetic field that's produced, right? As I go around this loop right here. And to understand how that magnetic field's produced, we use Ampere's law. Ampere's law basically says the integral of B dot dl, or B dot ds, I use ds usually. If I do the line integral of B dot ds, that this is equal to mu naught multiplied by the current that's enclosed. And what this means, and is something, I've mentioned this before, I enclosed represents the current passing through or piercing the current passing through really any surface that's bounded by the path. And in this case, my path would be this circle right here. Whoops. This is my path, basically, around which we can use this integral to solve for B, right? And just to run you back through what that calculation would be, because we don't use this very much, suppose that this has a radius r, and I say that because of the way that that current's flowing, I suspect that there's a magnetic field that points in this direction here. Okay? So I say, well, if B is this way, and ds is pointing in the same direction, then what we can do is we can say that this whole integral right here basically just becomes b times 2 pi r, right? And then the right-hand side just becomes mu naught multiplied by the current, and then we end up getting the magnetic field is equal to mu naught multiplied by the current flowing in the wire divided by 2 pi times the distance away from the wire, right? We've used that before in calculations, and Ampere's law shows us how to get it, right? Now, what did we do there? Well, we said the current enclosed was just I, basically. But the tricky thing about this is that the current passing through any surface bounded by the path. So what surface did I choose? Well, I basically chose this surface here, right? Like, I thought of it as a ring, and the surface that I chose was basically just the circle here, right? The filled-in circle around my wire. That's my surface, right? And that is a surface that's bounded by the path. The path being this purple ring right here. I guess my question to you guys would be, can you imagine any other type of surface that's also bounded by that path? When you think about a trampoline? I have a circular path, right? The simplest surface that's bounded by this path would just be a circle. Do you guys agree with that statement? But if I turn it sideways, so I'm looking at the edge of my circle, and that's my path now, what other type of surfaces would be bounded by this path? Does that make sense? Another surface that would have its edges as being this path. I don't know, is the question too complicated? It's okay if it is. I know, maybe I should write it out. I probably should. I can't always assume that I have your 100% attention all the time, because it can be very easy to, like, lose train of thought. But I'm asking basically, like, a dome. That's right, Quincy. A dome. So my path instead could be something like this. Think of like half of an egg, basically. Like half of an egg. Or think of, whatever you want. A net, maybe? That surface would also be bounded by the path, but now it's kind of open on this side, right? You see the difference? It's the difference between a path where I say this is my surface versus a path where I say this is my surface. Does that make sense? So we could basically do this. I could draw a dome. I want to pick a different color to do this. Which one of these is redundant? Maybe red or something, or purple. I can basically draw a dome around my capacitor now. You know what I mean? And now this is basically going to be my surface that I have to worry about. Now, why does that matter? It matters because of this statement right here. The current enclosed is the current passing through any surface that's bounded by the path. If we choose a path like this that goes around my capacitor, there's no current that flows from here to here, is there? There's no current that actually flows in this regime. So it would appear that Ampere's law is somehow incomplete. Because of the fact that I can choose any surface I want, in the case of a capacitor at least, it feels as if Ampere's law isn't telling us the full story. Now that I've drawn it and we've talked about it, I think it's safe that I can actually bring a very good version of the drawing that I just tried to make. So, what I'm trying to draw is this, basically. There we go. You have the path for Ampere's law right here, right? You've got your conduction current flowing in here. It charges up your capacitor plate. You have an electric field that's produced in the regime between, but no current actually flows from one side of the capacitor to another, right? And that means that if I choose this bulging surface right here, there simply is there's no current enclosed anymore. Can you guys see that? I don't know how well you can see it. The current enclosed basically appears to be 0. Okay? Which would imply that this should lead to the magnetic field being 0. It's like there's no current, why would there be a field? Does that make sense? Like, everything that we've learned about magnetic fields is that they're produced by currents, right? You need to have a current-carrying wire, or you need to have a moving charge. Those things will produce magnetic fields, right? Well, we have a current-carrying wire, and we know for a fact that there is, in fact, a magnetic field in this region right here, right? We know for a fact, wait, it actually goes the other way. It goes in the direction of DL, yeah. We know for a fact there's a magnetic field here, right? But Ampere's law would imply that if there's no current enclosed, then there's no magnetic field. Do you guys see the problem? Is the problem, like, clear enough for you? Yes, no? This is very complex. I understand it's not. It's tough. This is tough stuff. So this is what Maxwell did. He said, what if he's like, I know there's not actually current that flows between these 2 points, but what if we just imagine that there was for a second? And what we do is, let's say that let's call this type of current displacement current. And let's think if it's possible that we can imagine a way that this displacement current flows basically from here to here somehow. Not like conduction current. Okay, so I sub C represents what's called conduction current. This is some other type of a current that seems to flow through space, maybe. If we call ID the displacement current, then what we can do is we can say, well, we know that at a moment in time on our capacitor plate, that the charge on the capacitor plate, Q, is equal to C multiplied by the voltage in the system. And then we can say, well, for a capacitor plate, if it's a parallel plate capacitor, we know that the capacitance of the capacitor plate is given by epsilon naught, assuming that the region in between is just air or space, times A divided by D, where D is the distance between the plates here. That's D. And then we plug that into, and then we also know, what else do we know? We also know that the EMF between the plates, or the voltage on the plates, is equal to the electric field in the plates multiplied by D. So the charge on the plates at a moment in time then is going to be given by epsilon naught A over D. That replaces the capacitance. And then for the voltage, you replace the voltage with E times D. Right? The D's cancel, and we end up getting epsilon naught times E times A. That's the charge. And then we notice something. What's E times A, actually? When we take electric field and we multiply by area, what do we get? So area in this case is the area of this plate right here. And the electric field is the electric field in this region right here. You get flux, right? So this is actually epsilon naught times electric flux. And now, if I want to define what my displacement current would be, well, if you have charges that are building up on the plate, what you have is an electric field that's increasing over time. That's really worth typing out, at least in saying that. It's like, while... No, come over here. There we go. While... So you have this changing electric field, basically, right? While the plate's being charged, there is an electric field in the region between the plates that is growing. It's changing, right? And so what we want to do then is we want to say, define the displacement current to be related to the time rate of change of the charge. That is to say, we know that current is dq dt. So if we do that in this case, this is what we're going to get. We're going to get epsilon naught multiplied by d phi dt, assuming that epsilon naught is a actual constant. This is displacement current. It's the time rate of change of the flux, the electric flux. Okay. And then what we can do is we can take Ampere's law and we can write it in a more complete way. Now what Ampere's law is going to state is mu naught multiplied by the conduction current plus the displacement current. Both of those together are going to be combined together to give you the B dot ds. So this says the integral of B dot ds is equal to mu naught multiplied by conduction current. Okay, for that, we're just going to put I right here. Plus displacement current, but displacement current is given by epsilon naught times the time rate of change of the electric flux. That is the more complete version of Ampere's law, and this is referred to often as the Ampere-Maxwell law. Okay? Now, we can actually tie that together with something else that we just learned about. So, if you just look at those two equations, right? Do you notice some similarity? You see some things that are the same? The left-hand side in both equations is a line integral. In this case, it's magnetic field. In this case, it is electric field. On the right-hand side, the two equations have change in electric flux here and time rate of change of magnetic flux right here. Now, you can imagine that we can make these equations perfectly symmetric in a way if we just had one other term. We can make it perfectly symmetric if only we just had one more term right here, okay? What would the other term be? Well, it'd have to be mu naught or something. Maybe not even mu naught. Maybe it's going to be epsilon naught or something, multiplied by some type of current, but in this case, it would have to be magnetic current. Okay, but the problem is this doesn't actually exist. There is no magnetic current because there are no magnetic charges. They don't exist. So as a result, we have to use the form as it was before. Right? So we basically just get, there is a similarity, it's just that it's basically 0 plus this. Okay? But you can see, can you see the complete similarity right here? Notice that what these equations basically say is this. If I have a time rate of change of electric flux, that is to say if electric flux changes in time, I'm going to produce a magnetic field, right? And that magnetic field is going to be circular in nature. That's what this says, because it's a line integral. It's going to be circular in nature. If I have a time rate of change of, if I have magnetic flux that's changing, I produce an electric field. Okay? These two equations describe all of electrodynamics. That is to say, how systems behave when charges are moving. And what they tell us is that a change in electric field produces a magnetic field. The change in a magnetic field produces an electric field. Okay? You guys have any questions? So what I want to do now and for the rest of the class is to specifically describe all of Maxwell's equations together. So the other two Maxwell equations that we have is basically electric flux is equal to charge enclosed divided by epsilon naught, and the other one is if I take the magnetic flux, it's always equal to 0 through a closed surface. Those four equations, these are Gauss's laws. Those four equations together are what we call Maxwell's equations. And you can split it up into two forms. Basically, these two here talk about what's called electrodynamics, or what we call electromagnetism. and these ones refer to statics, basically. Static systems in which the electric field isn't changing in time, right? Now notice something else about this, by the way. It's not completely fleshed out with the way I have it written here. Flux in general, right, is equal to whatever the field you're talking about is, dot dA, right? So notice this. There's another way to write these bottom two equations right here, right? We could just write them as magnetic flux through a closed surface is equal to 0, and this one says basically electric flux, right, is equal to that, right? So these things really come together really nicely when you realize that what Gauss's law does is it tells you the value of what the flux is going to be in a static situation, right? And I take that and I go think about this one. Ampere's law tells me, well, what happens when the flux changes, basically, right? And I want you to think about this in terms of like I want you to go back and like think about 1A for a second. What do we do in 1A? We learn about how to describe where something is, position, right? And then we find out that when we take the derivative of that, we get velocity. And when we take the derivative of that again, we get acceleration, right? And once we know about acceleration, we're like, well, what causes acceleration? And the answer is forces, right? And you just go from there, right? There is a huge amount of similarity in Maxwell's equations in the following sense. They tell you here about what happens when flux doesn't change. Static situation, right? And they tell you up here what happens when the flux does change. And what happens is that when the flux changes, what do you get? You get a magnetic field. When magnetic flux changes, you get an electric field. Okay? That's what they say. That's what these equations say. Can you see the circular nature of that? Can you see how... Here, let me zoom out just a little bit. So look, basically, Faraday's law tells me if magnetic flux is changing, you get an electric field. If electric flux changes, you get a magnetic field. Okay? But what if your magnetic flux was changing, let's say, in a sinusoidal way? If magnetic flux changes in a sinusoidal way, you're going to get a changing electric field, right? What do I mean by that? How would you do this? Well, it's pretty simple. We've already learned about AC circuits, right? We've already learned about AC circuits, right? So if I have a current that's given by, some I max cosine omega t, and it's flowing through a solenoid, then, my d I dt is going to be something, like negative I max omega times the sine of omega t. But then this d I dt we saw before basically can lead to an EMF that's induced. And in this case, the induced EMF is going to be kind of proportional to this sine of omega t. But we also found out that if we take the EMF and we divide by 2 pi r, that you get an electric field. And now this electric field is going to vary in time. And it's going to vary in time as some Emax times sine omega t, maybe divided by 2 pi r or something. I don't know. So having the current change in time means you also have a magnetic field that's changing in time. Okay, the magnetic field is going to be proportional to some Bmax times cos omega t. Okay? This is why I'm trying to bring this all home here. It's like, if I have a situation in which the magnetic flux changes in a sinusoidal way, because the magnetic field is changing in a sinusoidal way, you get a changing electric field. But that changing electric field that you get, it's also varying in a sinusoidal way, right? Which means that when I talk about the way this all ends up working out, there's like a circular thing that happens here, right? So you get magnetic flux changing in a sinusoidal way, you get a changing magnetic electric field, but specifically you get an electric field that varies in a sinusoidal way as well. And then you basically just do the exact same thing down here. You say, okay, well now, as a result of that, you now have a changing a flux, an electric flux. It also varies sinusoidally. Is sinusoidally not a word? Or am I just spelling it wrong? This is not a word. How do you get magnetic field to change sinusoidally? Oh, it's easy. Look, here. All you need to do, right? Where's our magnetic field? See, that's the magnetic field, right? There it is. There's the magnetic field for a solenoid, right? All you need is the current to vary in a sinusoidal way. How do you do that? AC circuit. AC circuit will automatically do it for you, right? All right. And how do you get that? Well, you use a generator. Generators, we can talk more about that. We have in the past, but just want to kind of drive this home. So if the magnetic flux changes in a sinusoidal way, you get an electric field that varies sinusoidally. As a result, you have an electric flux that induces a magnetic field that varies sinusoidally. This has the effect of going back to this, right? So it's like 1, 2, and then 3, and then 4, and then it's like, then repeat. Something like that. Does that make sense? It's 5. This would be 5, wouldn't it? Whatever. Magnetic flux changes. You get an electric field that varies sinusoidally. As a result, you have an electric flux that, changes. So it induces a magnetic field that varies sinusoidally. Go back to 1. Do you see what I'm saying here? It's like a circular process, basically. This is effectively what an electromagnetic wave is. This is what light is. Maxwell's equations basically allow him to understand what light is. And I'm going to show you partially how that works by considering just this little piece right here. All right. So mu naught times epsilon naught. What I want you guys to calculate is the following. If I take... I think this is what I want you guys to do. I want you to calculate what this is equal to. So mu naught is equal to 4 pi times 10 to the negative 7. Okay. If we multiply this times epsilon naught is equal to 8.85 times 10 to the negative 12. I think this is the one that's like coulombs squared divided by... No, I can't read. It's 1 over... It definitely has to have newtons in the denominator. Yeah, it's coulomb squared over Newton meters squared. Okay. Can you guys calculate what you get if you do that? And we'll pull it up onto the E-Web calculator. E-Web. That's what you get. Something on the order of that's what you get. And if you look at the units here, so we have, what is it, Teslas, meters divided by amps, and we're multiplying by coulombs squared divided by Newton meters squared. So one of the meters cancels out. Again, I think Tesla was equal to, it was like Newton divided by amp meter. So you plug that in here, you've got newtons divided by amps times meters, multiplied by, well, one of these meters is going to cancel out. We still have coulombs squared here. We're dividing by newton and then just 1 meter if we cancel out that one and that one. And now what we have left is, sorry, Tesla was newton over amp meter, but that would be times 1 over amps. So there's also another 1 over A here as well. So basically, or we could just do A squared, right? Okay. But then A squared, okay, so the newtons cancel, right? The coulombs are going to cancel as well because an amp is a coulomb per second, or a coulomb is amp seconds, however you want to do it. How do we want to do this? So newtons divided by, so amps is basically coulombs squared over seconds squared. And then you've got coulombs up here. And we're dividing by newton meters. So I'm pretty sure what we're going to get, oh, squared, there's a meter there and there. So I'm pretty sure what we're going to get is basically seconds squared over meter squared. Does that look right to you guys? But the thing is that this whole thing is basically to the negative 1/2 power. So this quantity happens to be exactly equal to this number, which is a speed, and this is what's known as, does anyone know what that number is? Certainly some of you guys immediately recognize what that is. It's the speed of something. Yeah, Eric knows what it is. It's the speed of light. Now, why did I do specifically this? Ooh, boy. Whatever I just did. Push escape. Why did I specifically do this? Oh my god, I see what's going on now. It's because of this thing. It really doesn't like when I interact with this text box. This quantity here, why did I know to do that? Well, just to show you where it came from, I noticed that it showed up in that term right there, basically. And what we're going to do probably next time is we're going to solve Maxwell's equations, because they basically are a set of differential equations, effectively. And we're going to see that the magnetic field and the electric field, now this is the part where if you took 1b, you're in a good shape here, but if you didn't take 1b, you might not know what I'm about to say here. We're going to solve these equations, okay? And what we're going to do is we're going to see that the speed of the, well, what we end up getting is we're going to get what's called a wave equation. And the speed of the wave is going to be given by this expression right here. Okay? By this expression here. So we'll prove that next time. But this was something that Maxwell figured out. I don't know the order in which it was discovered. Like, I don't know if he knew originally that this quantity was, I don't know if he already knew that this quantity was equal to the speed of light. I think he did. But regardless, this is what we're going to be doing over the next week or so, is proving how it is that Maxwell's equations show that light is an electromagnetic phenomenon. And this is the first hint of it. The fact that the speed of light pops out of here, a number that was very well known during the time of Maxwell, something that was very precisely known during the time of Maxwell. The fact that the speed of light just naturally pops out of these equations is very surprising, I would say. Like, what Maxwell set out to do was to unify electricity and magnetism, to show that they're two different aspects of the same thing. But he ended up, in addition, proving that light itself turns out to be part of the same phenomenon, right? Light, like just light, like what you see. Every time you see light, you're actually seeing an electromagnetic phenomenon. There are quite literally electrons in your eyeball that are reacting to changes in electric and magnetic fields around them produced by these light waves, and that's how you see things. And it all comes out of little circuits. You know, if you think about where we've been this semester, right? We started off looking at simple circuits where you have like a battery and some current flowing. We started to make things more and more complex by doing things like saying, okay, well, what if I have a magnetic field that's changing in space or time? Like, what does that do? And it turns out that it induces currents. But those currents are actually produced by electric fields. That's what we learned today. And so we start to see that there's quite literally this program is really struggling to catch up here. I guess I could close this, would probably help. And I could probably close this and it would probably help too. But yeah, so that's Maxwell's equations in integral form. A hint at the fact that they tell us something about light, and that light, it has to be some kind of electricity and magnetism kind of phenomenon, basically. An electromagnetic wave, as we say. I think that's all pretty neat. Okay, I went through that really fast. If you guys have any questions at all, please feel free to ask. You guys have any questions?